Welcome to WikiPodcast. Welcome to the deep dive. Today we are launching into, well, a set of ideas that I honestly find mind-bendingly beautiful, Maxwell's equations.
Ah, yes, a cornerstone.
They really are. And, these aren't just some dusty old formulas. They are fundamental laws that completely reshaped our understanding of the physical world.
They absolutely did. We're talking about the mathematical language that brought together two forces that seem totally separate, electricity and magnetism, into one single coherent theory.
Right.
And in doing that, they basically laid the groundwork for almost every piece of modern tech that uses those forces. Think power grids, radio, Wi-Fi, all of it.
So our mission for you in this deep dive is to maybe cut through some of the math complexity and really get the core insights. We want to understand what these equations mean, how they manage this incredible unification, and what amazing things they predicted.
Yeah, it's really about seeing the universe in a new way, understanding these invisible fields and forces all around us. We'll be looking at the work of James Clerk Maxwell back in the mid-19th century. He was building on the work of giants, people like Faraday and Ampere.
Okay.
But it's interesting, while Maxwell developed the core ideas, the really elegant, compact form of the equations we often see today, that's largely thanks to Oliver Heaviside later on.
Ah, right, giving them that sort of vector calculus look we recognize.
Yeah.
So the goal here is that by the end of our chat, you'll have a solid conceptual feel for these laws and understand why there's such a huge deal in physics and technology.
Exactly. Let's dive in.
Okay, so let's unpack this. At their heart, Maxwell's equations are, four key statements about how electric fields, we call them E, and magnetic fields, B, behave.
That's right. Four key statements. They tell us where these fields come from, their sources, and also how they interact, how they influence each other.
Kind of like the rule book for electricity and magnetism.
Precisely. Think of them as the constitutional laws of electromagnetism. They govern everything from static cling to light waves traveling across billions of light years. They tell us about the sources, and this is crucial, the dynamic relationship, how changing one field can actually create the other.
Okay, that dynamic part sounds key.
Yeah.
So let's take them one by one. The first one, Gauss's law for electricity.
Yeah.
What's the big idea here? What's it telling us about electric fields and charges?
Well, the core idea is simple but really profound. Electric charge is the source of the electric field. That's it.
Okay.
This law tells us that electric field lines, they start on positive charges and they end on negative charges. If you picture a positive charge, the field lines just radiate outwards from it.
Like spokes on a wheel or a cosmic sprinkler. Maybe.
Oh, yeah, like a sprinkler. Field lines spring out. Gauss's law makes this precise. It relates the total flow, a technical term is flux of the electric field, out of any closed surface, like an imaginary box you draw in space.
Right.
It relates that outward flow directly to the total electric charge inside that box. More charge inside, more field lines poking out. And this counts all charges, whether they're free or, bound up inside atoms in a material.
Got it.
Yeah.
So electric fields start and stop on charges. Simple enough.
Mhm.
Now, magnetism. Does it work the same way? Are there magnetic charges, like isolated north or south poles?
This is where it gets really interesting. That's one of the most striking differences. The second equation, Gauss's law for magnetism, gives a very firm answer. No.
Yeah.
No magnetic monopolars. No isolated north poles or south poles exist, as far as we know. You can't have one without the other, unlike positive and negative electric charges, which you can separate easily.
Right, the classic example. You snap a bar magnet in half.
Yep.
You don't get a north piece and a south piece. You just get two smaller magnets, each with both a north and a south pole.
Magnetic field lines, they behave differently. Unlike electric field lines, they never start or end. They always form continuous closed loops.
Always loops.
Always loops. They come out of the North Pole, curve around through space, go into the South Pole, and this is important, they continue inside the magnet to make a complete loop. So Gauss's law for magnetism says the total magnetic flux through any closed surface is always zero. Because for every field line going out of the surface, there has to be one coming back in somewhere else on that surface to complete its loop. We say the field is solenoidal.
Okay, that's a fundamental difference then. Electric fields start to end on charges. Magnetic fields always loop.
Okay.
So, the third law, Faraday's law of induction, sometimes called the Maxwell-Faraday equation. This one starts linking the two, doesn't it? It's about changing magnetism, creating electricity.
That's exactly it. Faraday's big discovery. A changing magnetic field produces an electric field. But not just any electric field. It creates a specific kind, one that curls or swirls around the area where the magnetic field is changing.
Oh, like if you wave a magnet near a loop of wire, you get a current flowing.
Yes, that's the classic demonstration. Moving the magnet changes the magnetic flux, the amount of magnetic field passing through the wire loop. And that change in flux induces an electric field that pushes the electrons around the wire, creating a voltage and a current.
Okay.
This is the fundamental principle behind electric generators, rotating magnets or coils to constantly change the magnetic flux and generate electricity. And it's not just small scale. The source mentioned how huge geomagnetic storms, basically, big changes in Earth's magnetic field over time, can induce electric fields strong enough to cause major problems for power grids.
Wow. Okay. So a changing magnetic field can induce a swirling electric field, sometimes powerfully enough to affect the grid. That really connects the abstract idea to the real world, which
Sure.
I guess brings us to the fourth equation, the Ampere-Maxwell law. Now, Ampere's original law linked currents to magnetic fields, but Maxwell added something crucial, didn't he?
He absolutely did. And this addition, this is arguably where the biggest leap towards understanding light happened. So, Ampere's original law said electric currents moving charges create magnetic fields that curl around them. Think of the magnetic field circling a wire with current flowing through it.
Right, the right-hand rule stuff.
Exactly. But Maxwell realized this wasn't quite the whole story, especially when things were changing over time, like when charging a capacitor where there's a gap the current can't physically cross. He saw an inconsistency. To fix it, he proposed and added a new term. He called it displacement current.
Displacement current. That sounds like something's moving, but you just said there might be a gap, like in a capacitor. So what's displacing an empty space?
Yeah, that name is a bit of a historical artifact, maybe slightly misleading today.
Oh.
It's probably better to think of it not as a current of moving charge, but as representing the effect of a changing electric field. Maxwell's genius was realizing that a changing electric field also acts as a source for a magnetic field, curling around it, just like a conventional current does.
Wait, so a changing electric field creates a magnetic field.
Yes.
That sounds symmetrical. Didn't Faraday's law just tell us a changing magnetic field creates an electric field?
Exactly. You've hit on the crucial point. That symmetry is key. Maxwell adding this term completed the symmetry between electricity and magnetism. The seemingly small mathematical addition, it fixed the theoretical problems, and much more profoundly, it predicted something absolutely extraordinary about what could happen in empty space, far from any charges or wires.
Okay, I'm intrigued. What was the extraordinary prediction?
This is where it gets really, really cool. When you take these four complete equations and you look at what they say happens in a vacuum, just empty space, no charges, no currents, they simplify quite a bit. And when you manipulate those simplified equations mathematically, you can derive wave equations.
Wave equations. Like the math that describes ripples spreading on a pond, or sound waves.
Conceptually, yes, exactly like that. The math showed that disturbances or oscillations in the electric and magnetic fields themselves could propagate outwards through empty space, carrying energy as waves.
Wow, okay, so waves of electricity and magnetism. And did the equation say how fast these waves would travel?
This was the absolute stunner. The speed predicted by the math wasn't arbitrary. It was determined entirely by two fundamental constants of nature that were already known from electrical and magnetic experiments. One related to electric fields, the permittivity of free space, and one related to magnetic fields, the permeability of free space. Maxwell plugged in the best-known values for S and mass.
What speed did he get?
He got a number, and that number was incredibly, astonishingly close to the speed of light, which had already been measured experimentally through various methods.
No way.
Yes way. There were experiments like one by Weber and Kohlrausch around 1855 that had measured a constant based purely on electrical and magnetic units, and their value was about 3.1 by 10 meters per second, which was known to be suspiciously close to the measured speed of light. Maxwell's calculation, derived purely from his E&M theory, landed right on that number.
So the speed that pops out of his equations for these electric and magnetic waves, it just is the speed of light. That can't be a coincidence.
It absolutely wasn't. This was the earth-shattering moment. It led Maxwell around 1861 to propose the revolutionary idea. Light itself is an electromagnetic wave. It's not some separate thing. It's literally a vibration and oscillation traveling through the electromagnetic field, described perfectly by these four equations. A complete unification of electromagnetism and optics, just like that.
That's incredible. So how do they keep going in empty space? There's no air or water, no medium to wave in.
That's the beautiful, self-sustaining dance the equations predict. Remember the symmetry. The changing electric field creates a changing magnetic field. That's the Ampere-Maxwell law with the displacement current term.
Okay.
And then that changing magnetic field immediately creates a changing electric field. That's Faraday's law.
Ah, so one creates the other, which creates the first one back again.
Precisely. It's a continuous leapfrog, a self-propagating cycle. The changing E field makes a B field, changing B field makes an E field, and so on, allowing the wave to travel through completely empty space at this specific speed, see the speed of light.
And the visible light we see is just one tiny slice of this whole phenomenon.
Just a tiny slice. These electromagnetic waves exist across a huge range of frequencies and wavelengths, the electromagnetic spectrum. You've got radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays, gamma rays. They are all fundamentally the same thing.
Wow.
They're all electromagnetic waves propagating according to Maxwell's equations in a vacuum. The only difference is their frequency or wavelength.
And the E and B fields in the wave, they're oriented in a specific way.
Yes. The math shows that in these waves, the electric field vector and the magnetic field vector are always perpendicular to each other, and both of them are also perpendicular to the direction the wave is actually traveling. They oscillate together, in phase, reaching their maximums and minimums at the same time and place as the wave moves along.
It's mind-boggling that this understanding underpins so much. Wireless communication, radar, how we get TV signals, how light travels from stars. It's all built on this wave nature described by these four laws.
It really is. It's the absolute bedrock of modern electrical engineering, optics, and much of physics.
Okay, so these equations are clearly incredibly powerful. They describe so much of our world, but are they the final absolute word on electromagnetism? Are there limits? Places they don't quite capture everything?
That's a really important question. And the answer is, well, Maxwell's equations, as we've been discussing them, are the classical description. They are fantastically successful, incredibly accurate for, macroscopic phenomena, things bigger than atoms, and for fields that aren't absurdly strong.
So classical, meaning before quantum mechanics.
Exactly. Their main limitation is that they don't fully incorporate quantum mechanics. Phenomena that reveal the particle nature of light photons or things that happen in extremely intense electromagnetic fields, those need a more fundamental theory.
Which is?
That theory is quantum electrodynamics, or QED. It's basically the quantum version of Maxwell's theory. Maxwell's equations are what you get from QED when you zoom out, when quantum effects become negligible, like when you have huge numbers of photons behaving collectively as a wave, or when fields are relatively weak. They can't, for example, explain the photoelectric effect on their own, or more subtle quantum things like entanglement involving electromagnetic fields.
Okay, so they're a brilliant approximation for the everyday world and most engineering, but the ultimate description is quantum. Makes sense.
Right. And another nuance is how they're written. We've mostly talked about the microscopic equations, which deal with the fundamental fields, E and B, and total charges and currents everywhere. But there's also a macroscopic version that's often more practical when dealing with fields inside materials.
How does that work?
It sort of averages things out over the atoms and introduces auxiliary fields, often called D and H, which account for how the material itself responds to the E and B fields. It simplifies calculations in materials but requires extra information about the material's properties. It's also worth noting just how well these equations fit with Einstein's relativity. Even before Einstein, the structure of Maxwell's equations had this property called Lorentz invariance built in. They already worked correctly regardless of how fast the observer was moving, which was a major clue that led towards special relativity.
The fact they hinted at relativity is just amazing in itself. You also mentioned something about them seeming overdetermined mathematically. Like too many equations.
Yeah, it's a neat point about their structure. If you just count, you've got vector equations, which represent multiple scalar equations, and it looks like you might have, say, 8 equations for only 6 unknown field components. X A as Bx by B. But it turns out the two Gauss laws aren't fully independent of the other two.
Oh.
You can actually derive Gauss's law for electricity from the Ampere-Maxwell law if you assume charge is conserved, which is also embedded in the equations. And you can derive Gauss's law for magnetism from Faraday's law, again, assuming charge conservation and also assuming that there are no magnetic monopoles. It just shows how beautifully consistent and interconnected the whole system is.
And that assumption about no magnetic monopoles, that's explicitly in Gauss's law for magnetism, right?
It is, yes. That law, stating zero net magnetic flux through a closed surface, is mathematically equivalent to saying there are no magnetic source charges, no monopoles. If we ever did find convincing evidence for magnetic monopoles,
Which people have looked for.
oh, extensively for decades, if they were found, it would actually require modifying two of Maxwell's equations, Gauss's law for magnetism and Faraday's law. Interestingly, adding monopoles would make the equations look even more symmetric between electric and magnetic fields. But despite all the searching, no fundamental magnetic monopoles have ever been confirmed. There are some cool exotic effects in certain materials that can mimic monopoles' behavior, but they're not fundamental particles.
So it boils down to this. From just 4 elegant equations, James Clerk Maxwell pulled together electricity, magnetism, and light. He gave us this unified picture of the electromagnetic universe. It's really a stunning intellectual achievement.
It truly is. It's such a powerful demonstration of mathematical physics. You take observations of forces that look separate, you find the mathematical laws that describe them, and suddenly those laws reveal deep connections and predict entirely new things, like the very nature of light itself, traveling as a wave at speed c. These equations are absolutely foundational to our modern world and how we understand the cosmos.
It really makes you wonder.
Doesn't it? You know, given that almost everything we know about the distant universe, about stars, galaxies, nebulae, comes to us as light, as electromagnetic waves that have traveled for maybe millions or billions of years, how does understanding that this light is described perfectly by these 4 classical equations deepen our appreciation? How does it connect the physics in our phones and power lines to the grand scale of the cosmos itself?
Thanks for listening. Write us your opinion on what surprised you most about the connection between electricity, magnetism, and light revealed by Maxwell's equations in the comments. Subscribe to the channel to help more listeners reach our episodes. Thank you, and have an amazing day.